Alright, so I've switched everything back the way it was. We've just finished doing the computer simulation for genetic drift. I hope that you came out of that conversation understanding that genetic drift is a random force, meaning that it's not possible for us to predict exactly what's going to happen. We have some vague ideas. The smaller the population is, the more likely we're going to fix alleles, which means we're losing genetic diversity from the population if the population is sufficiently small. However, we don't know specifically which alleles we're going to lose, and therefore it's a random-like force. Okay? When I think about genetic drift, I often think about it as a bucket of alleles that exists within a certain population. So I have my population of alleles in the bucket, and each year I take a random sampling of alleles out of the bucket to make next year's individuals, and then those alleles found the new population in the following year, from which I'm going to sample out more alleles to make the next generation, and so on. So the genetic drift phenomenon acts at the level of populations, right? It has to do with meiosis and how these alleles are sampled. Okay? There are other drift-like evolutionary forces, and because they're drift-like, they're classified in this big category of genetic drift because they all involve sampling error. In the case of genetic drift, it's sampling error at the level of meiosis, right? Which alleles get selected for the next generation. I'd like to do two other drift-like forces with you. We're still dealing with sampling error, but where this sampling error occurs is going to be a little bit different. So let's start with our initial population here. Let's make it large. And from this large population, we're going to select a number of individuals. Now, they have alleles with them, so by taking these individuals and moving them someplace else, we are in effect moving those alleles someplace else. So we're going to use the small number of individuals here, referred to as founders. These initial colonists or founders will found this new population. In our initial population, there was a certain frequency of an allele. We randomly sampled alleles from the population by sampling out individuals. These individuals have those alleles, and my expectation is, because I sampled such a small number of individuals, the frequency of this A1 allele in this new population is not going to be the same as in the original population, right? That's where the sampling error comes in. This difference in allele frequency here with respect to the original population is called the founder effect, because what we're talking about is differences in the allele frequency in the founding population relative to the original one. Okay? All right, so let's work through this. We can use this as a way to kind of check our ability to work with the Hardy-Weinberg equilibrium, and also a way to check our ability to determine allele frequencies. So I have a little exercise here on the founder effect. All right, let's go to 1814, and the founders, there are going to be 15 of these founders, and they're going to found a British settlement on a group of small islands between Africa and America. One of these colonists carries the recessive allele that causes retinitis pigmentosa. They carry it, which means they're heterozygous, and the blindness that retinitis pigmentosa causes only affects homozygous recessive individuals. So I've got 15 colonists, and one of them is a carrier. So 14 of them are homozygous dominant. Let's make R the wild type allele. And one of them is heterozygous. They have one wild type and one retinitis pigmentosa allele. Okay? So, what's the frequency of little r in these colonists? Okay? Feel free to stop it, work through the math, and then come back. I'm going to go ahead and do the math and assume that you've taken some time to think about this a little bit. Okay? So, if there are 15 colonists, that means there are 30 alleles in the bucket. And of these 30 alleles, one of them is the retinitis pigmentosa allele, while 28 plus 1, 29 alleles are the dominant allele frequency. All right, so I'm just going to pull up my calculator here, or maybe not. I'm going to pull up my calculator. All right. I don't want that. Leave me alone. All right, 1 divided by 30 equals 0.03. So that's the allele frequency for the retinitis pigmentosa allele. Okay, that's the allele frequency. All right, now let's fast forward into the future. Of the 240 descendants living on the island in the late 1960s, 4 had the disease. Okay? 4 had the disease. And the frequency of this allele remains 10 times higher on the island than in the populations from which the founders came. So if we go here, we have 240 descendants. And we're saying that 4 have retinitis pigmentosa of these 240. Now, these 4 individuals, if they have retinitis pigmentosa, they have to be this. The other 236 descendants are wild type. What's their genotype? Well, there are 2 ways to get this. You could either be homozygous dominant or heterozygous, which means we can't just think about the allele frequency based on alleles in the bucket, because we really don't know whether these 236 individuals are contributing only dominant alleles or a mixture of both dominant and recessive. So we're going to have to fall back on Hardy-Weinberg. So Hardy-Weinberg says that the expected frequencies of the genotypes is given by this. Well, this individual is a genotype, okay? And that frequency is 4 out of 240. Right? That's the allele frequency. That's the genotype frequency here. Is that okay? 4 out of 240, that's 4 of these individuals out of all of the individuals in the population. Q squared is the frequency of the homozygous recessive. Well, we know that frequency, so that means that this is equal to Q squared. Okay? All right, so Q squared then equals 2 out of 140, 1 out of 60. So that means that Q is the square root of 1 over 60. Q is equal to the frequency of the little r allele. Okay, we've got to go to a different program this time. So equals 1 divided by 60 raised to the 0.5, 129. Okay? So, the frequency of the allele in the founders was 3%. Fast forward to the 1960s, the frequency of the retinitis pigmentosa allele is now 12.9%. So what accounts for this change in allele frequency over time? Well, the change in allele frequency from here to the 1960s is probably genetic drift, because this population here drifted over time, and by chance the retinitis pigmentosa allele was increased in frequency. Okay? By chance it was increased in frequency. Now, the text here also says that the frequency of the allele remains 10 times higher than in the populations from which it came. So if this is the original population in Britain, because it says British colony, I'm assuming that these individuals here that colonized were British, that means that the allele frequency now is 10 times higher than Britain, which means that the original allele frequency in Britain is about 1.3%. The difference between this number and this number is because of the founder effect, and the difference between this number and this number is genetic drift. Okay? The random sampling of individuals to found a new population, that's the founder effect. The same population over time, that's genetic drift. Okay? Now, the founder effect is very well studied. During the Age of Discovery, the European populations were sending colonists all over the world to set up these new populations. And as they set up these new populations, the individuals that set them up often had different allele frequencies than the founder population, hence the founder effect. But we paid a lot of attention to these because these founders often had particular genetic disorders that were not very common in the population, i.e., this population having retinitis pigmentosa, which was not very common, or the population that was founded in Nantucket, that's an island off of Massachusetts, by the early Pilgrims. A very small number of individuals founded that population, and by chance carried an allele for congenital deafness. The first deaf school in the United States was on Nantucket because a large percent of the population had this congenital deafness because of a founder effect. Closer to home, the Amish population in Pennsylvania has a recessive allele for a rare kind of dwarfism that's linked with polydactylism, 6 fingers instead of 5. And the idea is that the founders of this Amish population in Pennsylvania, small number of individuals, but by chance they happen to carry the allele that caused this condition, and it's in higher frequency than the rest of the population. Again, this founder effect. Okay? All right, so let's go back to kind of my main model for thinking about this. We have genetic drift, which is the population being used to refound itself over time. And over here, that's the founder effect, where we move individuals from one location to the other. There's another drift-like force that goes like this. I start with a large population, and then over time, the population gets squished down to a small number, and then over time, it goes back to a large number again. Okay? Now, what's important in this model is that whatever happens to shrink the population here has to be random. It can't be something that individuals can be adapted to, because that would imply a genetic basis for surviving, in which case we have natural selection. Instead, we have to indiscriminately take out individuals. So here is my population. That's my bucket of alleles right here. This is the frequency of these alleles, and they're showing us 3 alleles in the bucket. Like I said, populations contain lots of alleles. Mendel's idea of 2 alleles for any trait was a little off. There are hundreds. It's just that any individual can only have 2 of them. All right, here's generation 2. There's the frequency of alleles in the bucket. 20% tan, 50% green, and 30% fuchsia. Then I'm going to force this population through something bad. This bad here is called a bottleneck. All right, I'm forcing the population to shrink in size because of a force acting on the population that nobody's adapted to. I'm basically randomly picking out individuals from this population that will survive. And because I'm randomly picking them out, I'm randomly picking the alleles that they have. By chance, I didn't pick any individuals with tan alleles, and then when the population recovers, right, population growth takes us back to where we were, when the population recovers, there's no more of this tan allele left, and the allele frequency used to be 50% green, now it's 70% green. That's a change in the allele frequency, hence an evolutionary force. Okay? All right, okay with that? Now, these forces, what kind of forces are operating on the population that are indiscriminate, that individuals just can't be adapted to? Well, this could be something like a mudslide or an avalanche that takes out all of the trees that are on that hillside. Well, trees don't have adaptations to withstand thousands of tons of snow or mud. So which individuals get affected just depends on which way the avalanche goes. Some individuals are going to survive because by chance the snow went around them, whereas in other individuals are being wiped out by the snow. Hurricanes could be a good example of this. Fire, volcanic eruptions. War, in the case of humans, is a pretty indiscriminate force, right? Where you happen to be standing may allow you to survive the big bomb that got dropped on the city. Okay? Now, it's important that individuals don't have adaptations for these. Because if they have adaptations, then all we're doing is selecting for individuals that have the alleles. That's natural selection. This is not natural